We're here with Steve Gaddis, the manager for the Game Changing Development Program Office. Steve, how you doing?
Doing good.
So Steve, we have this whole technology campaign where the theme is technology drives exploration.
Absolutely, and I believe it.
What's that mean, technology drives exploration?
It means if you want to do these cool things that we haven't done before, we have to develop the technologies to go do them. We can't simply just keep doing what we've already done in the past, right? We've done some cool things, but we want new missions. We want to go farther than we've been. We want to drill down. We want to bring things back. So we need these new technologies.
Now with Game Changing, you're sort of a subset of the Space Technology Mission Directorate at NASA headquarters. And so what's the focus on Game Changing as opposed to the other technology subprograms?
We're the disruptive program. We're the DARPA-like program out of the 9. However, all the programs, they're looking for revolutionary and incremental developments in technology. But our associate administrator really wants us to take some risk. He expects a certain amount of failure in the activities that we're pursuing, the high payoff, high risk type activities. And so he'd like to see the risk take place with us instead of maybe in some of our sister programs where we're demonstrating on orbit or we're demonstrating on the International Space Station or we're demonstrating on a ride with another government agency or the commercial crew type folks.
So when you talk about specific technologies in your program, are you taking programs from scratch or are you getting programs from another group that have already been through a certain, mature process?
So it's a mixed bag. Some things we generate from scratch. However, what we like to see them get to a TRL, technology readiness level of around 2 or 3 before we pick them up. And in many cases, someone's done the basic research, whether it's industry or whether it's a university or whether it's some of our research centers. They've proved the concept. Getting from 3 to a TRL 6 or 7 is really where the challenge is, and that's where GCD fits, that mid-TRL range.
Now, when we talk about TRL, we're looking at a scale from 1 to 9.
1 to 9. 9 meaning it's flown in space multiple times, heritage. 6 or 7 means it's going to be demonstrated, or it was demonstrated in a relevant environment such as space.
And in your TRL range, it won't fly in space, but it will be tested here on Earth.
It depends, but that's primarily the focus. We do TRL 3 to 5 and 6, and 5 is a near relevant environment, could be a suborbital environment, but several things that we do also go on to station, right? So that's obviously in orbit, it's in space as well. So a small part of our portfolio does make it to space.
Now, what are some technologies in your portfolio?
Man, there's some really cool things. Some of which are far out, some are a little closer home. We're looking at wearable technologies, and that would be like in the old Star Trek days, when someone's got the comm on their shirt and they hit the comm and they can communicate. Others, it's relaying information back and forth. The astronauts need things like that. And we've been working on something called an exoskeleton. And essentially what this began to do was just provide exercise for the astronauts, right? And they got to take all that equipment up there. It takes space, volume, power, et cetera. But if we can take this one it compacts, it stores very nicely, and it can give them that resistance exercise. But then the reverse of that is if they had to be in a situation where they needed a little extra horsepower,
right,
it could give them that as well. That's been a spin-off to the Veterans Administration, helping wounded warriors get back into action. We're developing new robots, humanoid robots. Then in a particular area that's of interest to me is nanotechnology, which is just a blossoming field. They're making almost daily discoveries with nanotechnology. They'll take these carbon nanotubes, they'll mix them with a fluid, and then this fluid will end up with a new characteristic that they can apply to something. So we're looking at making materials out of these nanomaterials. We call them nanocomposites. And if we think composites themselves reduce mass and cost, this takes it another order of magnitude. So we're very interested in it. We're looking at nanosensors, very small sensors that you can put on something that can track your blood chemistry and report that out. Also, sensors that can be weaved into something that you can't even tell it's in the material because it's a nano-type sensor. We're looking at a COPV, which is a carbon overwrap pressure vessel, right? So it's a tank. And we'll take this nanomaterial and we'll wrap it over this aluminum inner structure.
To strengthen it? Or?
Yeah, to strengthen it. And it also reduces the weight because it doesn't all have to be aluminum. We've got one of those that's going to be flown on the sounding rocket next year. We're very excited about it. We're also looking at nanowires. We just set a world record with a nanowire with the most electrical conductivity ever demonstrated to date.
That's amazing.
I mean, it is amazing. It's groundbreaking.
It's game-changing.
It's game-changing.
That's right.
It really is. So we're looking at the nanowires. We're looking at the nanosensors. We're pursuing the nanocomposites. Really cutting-edge, cool technology. Lots of things like that.
You know, Steve, he's a real game changer. He did a great job giving us an overview of how NASA uses nanotechnology.
You know, one day I'd like to see how nanosensors will work in things like watches and phones.
Well, you've come to the right place because we had a chance to sit down with two important people who are using the cell phone and nanosensors.
Yeah, we had a chance to talk with Maya and Jessica about how NASA is incorporating this technology into cell phones and using them in different ways. But what I'm really curious is, can we really understand just how small this technology is to do just that? May I understand nano is small. So with nanosensors, I'm assuming you're dealing with really small sensors. But what exactly are nanosensors doing?
Yeah, nanosensors are a product of nanoscience and nanotechnology. When materials go to that small scale, their properties are fundamentally different from bulk materials. So scientists all around the world, have been working very hard trying to take advantage of this difference in properties between the bulk scale and the nanoscale and trying to make useful things, which are devices, systems and architectures, materials for a wide variety of applications, touching upon every economic sector, which is electronics, computing, materials, manufacturing, health, medicine, national security, transportation, energy storage, and I don't want to leave out space exploration.
I was going to say, that's a lot of stuff anyway.
Yeah.
You mentioned space exploration, so I'm wondering, how are nanosensors being used by NASA?
The nanosensors are being developed to replace bulky instruments NASA has been using. No matter what you want to measure, whether you want to measure a composition of a gas or a vapor, or you want to measure radiation, historically we have always taken bulky instruments. And remember, every pound of anything that we lift to near Earth orbit, it costs us about $10,000 a pound. The same 1 pound of anything would cost roughly about $100,000 a pound, for Mars and other missions. Okay, so we have an incentive actually to miniaturize the size of the payload. So that's why we want to move from bulky instruments to sensors. That's one reason. The second reason is, no matter where we go, okay, we don't have utility companies sitting there waiting for us. Okay, we have to generate our own power, and we have to be very wise how we use that power. So the sensors, not only they're small in size, but they also consume very low power. So that's why over the last decade or so, we've been working on developing nano-based chemical sensors, biosensors, and radiation sensors.
Now, when you're looking at these biosensors, and we're looking primarily for crew health, crew safety, what would they be used for?
What are the applications? Yeah, we've developed them for crew health and diagnostic purposes. That's our most recent project that we worked with the Game Changing Technology Office on. And so for that project, we developed this sensor to look at a variety of different protein biomarkers for cardiac health. And so when you're in microgravity, there's a lot of strain that's placed on the heart. So to monitor the health of the heart for our astronaut crew is critical. So that is the most recent technology that we developed for them. We've also worked on this sensor looking at microbial contaminants and the water supply. So this is an environmental kind of application for NASA to make sure that the water that the astronauts are drinking is actually safe to drink.
Now, when you're looking at the astronaut's heart, is it a sensor that you place on their body, or is it something they ingest, or what? How's
This is an external sensor that will take 1 drop of blood and be able to screen for a number of different proteins. And depending on the levels of proteins and which proteins are present, we can make an informed diagnosis of the health of the crew member's heart.
Do these sensors have a long shelf life, or is it something that lasts for a short period of time because of the complexity of the sensor?
It depends a little bit on how we fabricate them and how we package them. The sensor itself, without any kind of surface modifications done to it, has a very long shelf life. I have sensors in my lab that are probably 10 years old that I can still pick up and use today. What limits the shelf life of these types of sensors is we often introduce some sort of biological probe molecule on that surface. So depending on what that probe is, that's going to dictate the storage needs as well as the shelf life of the device. We've been placing a lot of emphasis on making probes that are very robust so that we can increase that shelf life for our missions, so that we're not looking to replace these sensors every 6 months, that we can actually keep them for years at a time and continually reuse them.
And one of the coolest things that you were showing us this past week was the fact that you have a cell phone technology adapted to these nanosensors. So you have an application that you developed on the phone that can actually be used in concert with the nanosensor.
So this was designed actually for the chemical sensor project. And this phone has a plug-in port on one side that contains the sensor chip, has a fan that will direct airflow from the environment over the sensor surface. And then just using the electronics that are part of the phone, we have a nice little instrument that will actually read what kind of chemical environment the sensor is exposed to.
Now, would you have multiple nanosensors within that adapter for the phone, or is it just one nanosensor?
So we have one chip, but these chips can be made with a number of different sensors. They can have hundreds of sensors. They could even have thousands of sensors on one chip, all working together to tell the user of the phone what the environment is.
Guys, that was some great information on nanosensors. I can definitely see how that is a game changer, because once it's commercially available, it will definitely change our lives.
I tell you what, we could have spent a whole show on nanosensors. That's how cool the technology is.
That's right, Chris, but we're only scratching the surface at looking at this technology. I had a chance to sit down with Jim Geyer, and he explained how NASA is using nanotechnology to develop better, stronger wires. Let's check it out. Jim, I understand that you're working with carbon nanotubes as a potential replacement for conventional wiring, but I didn't know wiring needed an upgrade. What exactly are you doing to improve wires?
Well, I don't think a lot of people understand that wiring really takes up a large amount of the mass in current spacecraft and aircraft. Like a 747 has nearly 2 tons of wiring in it, and the space shuttle had almost 300 miles of wire. This is a lot of weight, and so conventional wiring with copper is very heavy. Copper is dense, and it's also not very strong. And so we're looking for a way to have a better mechanical properties, actually, than conventional wires have.
So these carbon nanotubes, when you make a wire out of them, how do they perform in terms of strength?
They're much stronger, they're more thermally conductive, so you don't get hot spots and so on. They're very flexible. They're actually much more flexible than copper, and they don't fatigue. Fatigue is when you get a breakage from moving back and forth.
That's how I break wire intentionally sometimes.
Exactly. And in fact, they ran tests and they were not able to run enough cycles to actually break these carbon nanotube wires. They finally had to give up and go on to the next test.
Okay, so the carbon nanotubes are stronger and they're lighter. How do they perform in terms of conductivity?
Well, conductivity is the issue. It turns out that carbon nanotubes, while theoretically have a very, very high conductivity, to use them practically, you have to make these bundles, because an actual carbon nanotube is less than microscopic. And so to use them, we have to actually bundle them together. And when you bundle them together, you lose a lot of that conductivity.
And that's principally where your work is then. You're going to solve this conductivity problem.
That's our goal.
Okay.
Right. What we're doing is we are chemically altering the carbon nanotubes. We're doing a process called intercalation, which means to insert. And we are inserting halogen atoms. These are bromine, chlorine, iodine, in between the bundles. And when we do that, it makes the bundles actually much more conductive. And so what we're trying to do is get to the place where our conductivity is high enough that we can run these as electrical conductors. They're not going to be as conductive as copper, but because the wiring in aircraft and spacecraft is not limited by the conductivity, but by the strength, we're going to be able to save a tremendous amount of weight. We're in the early stages of our research, but we've already developed carbon nanotube wires that have a specific conductivity, that's a conductivity per gram, equal to copper.
Well, solution, problem solved. That's great. No, that's a good step, right?
It's a good step, but it's not the only step. Okay. Because right now we're working with very, very tiny amounts. I mean, milligrams of material, and we're going to have to work with kilograms of materials. And so we have both the process of our partners who actually make these fibers have to scale up so that they can make large quantities, and we have to scale up our chemical processes so that we can modify them.
Okay, so scaling up is actually the big challenge.
It is.
Okay, see, for a second I thought if I understood this properly, I'd understand how Peter Parker could shoot web, okay? But apparently with the scale-up issue, not even he could handle it at that.
I'm afraid not.
All right, well, appreciate it. I wish you the best of luck, and I hope soon to see copper wire. Well, I don't want to see them go away, but at least in terms of these aircraft and spacecraft, saving that weight and giving us all the conductivity we need.
I hope so.
It's interesting to see how NASA, as they improve on a technology, just how complex the process becomes. And I never would have thought about it, but creating nanowire is actually a groundbreaking or game-changing technology.
Yeah, and that's a cool area of research that Jim's working on. But another area that NASA's looking at is carbon nanotubes and overwrap pressure vessels. So what they want to do is they want to take a COPV, or a composite overwrap pressure vessel, and spin it with carbon nanotubes.
And those carbon nanotube composites are, as you said, very difficult to work with. So NASA is actually looking at a couple different approaches.
And I had an opportunity to look real closely at least one of those approaches. Let's check it out. We're here with Aslan Biagi, who's the project manager for Nanotechnology. So Aslan, tell us about what you're doing with nanotechnology.
Our goal is to actually use the nanotechnology and make lighter materials so that we can reduce weight on the vehicles and launch vehicles.
And I understand you have a big flight test that you're moving toward.
Yes, so our carbon nanotube reinforcement composites that we're developing in the nanotechnology project will later be placed on a composite overwrap pressure vessel, which will be launched on a sounding rocket.
Haven't we launched like composite overwrap vessels before? What's unique about this one?
So COPVs have been on NASA for a long time. The only difference here is that we're using carbon nanotubes instead of carbon fibers, which is the typical material that we use for the COPVs. Now we're transitioning into carbon nanotubes, and that's actually making the material 2 times stronger than carbon fiber and also lighter. And that's the game-changing part of it.
Tiffany, how do you guys prepare for a carbon overwrap pressure vessel test?
So we start off by taking the tensile strength of ring specimens, where we have an aluminum ring and they're overwrapped with a carbon nanotube yarn and resin in a composite structure. And the reason why we do this is to help us predict the load at where our composite overwrap material is failing. So the rings are speckle painted for digital imaging correlation, so we can better determine how and where the failure occurs.
So you guys actually plan in these tests to actually break the rings?
Yes, we test the bare aluminum rings first so we can get a baseline value of the load where the aluminum ring is failing, and then from there we could subtract the failure from the composite overwrap material from the baseline so that we can know the tensile strength of the overwrap material itself.
Have you done actually any tests? Do you know how successful or how strong this overwrap is going to be?
Yes, right now the first layer of material that we're putting onto the rings fell at about close to 600 pounds of force from that small overwrap material. The overwrap material that we're testing is only about 0.36 inches wide.
Nice. Mm-hmm. So you do test on rings as well as full tanks, is that correct?
Yes, the tanks are the end goal, but for everything that we're doing right now is for the ring test to prepare for the ultimate burst test, and that's actually when the tanks will be wound with this particular type of material.
You use that word burst specifically because you really want to pressurize the tank to the point of failure, which creates a burst.
Yes, correct.
I hope you're successful bursting the tanks.
Thank you. We hope that there's not going to be a really large knockdown in properties compared to carbon fiber composites. This technology at this level is still in the premature stages. We're just trying to help do as much research as possible on these preliminary tests so that we can further advance this technology and get it to the area where carbon fiber composites are currently.
So John, Tiffany gets a lot of data from these tests. How are you using that data to prepare for the upcoming flight test?
Well, what we've done is made sure that we've interacted with Wallop's sounding rocket experts to make sure that we capture the entire flight environment and all the design requirements for our COPV and bring those into the laboratory and have Tiffany duplicate the critical environments that the material has to operate in. This gives me data that I then use to size or dimension the COPV, determine how much nanocomposite is actually applied to meet the performance and safety requirements that Wallops has for their sounding rocket flight. We consider the vibration environments and the temperatures that a COPV will see and make sure that all the forces and loads that are applied to the COPV are accounted for in our design.
How will an improved technology, this game-changing technology, help future missions?
Well, we know that the carbon nanotube is one of the most strong and stiff materials known to man. If we can get that material into an engineering application, we could probably make much lighter spaceflight hardware than what we're doing right now. By adding this small nanotube wrap, we could easily increase the strength of the tank by a factor of 2, with only increasing the weight of the tank by perhaps 10%. So that's an enormous gain in strength.
We're back to continue our discussion on the processes to wrap the pressure vessels. We just saw one. Mia, tell us about another.
Okay, so what we've done here is taken a spool of carbon nanotube yarn, and instead of processing it in a large machine, we took the critical steps that we use in a large machine and downscaled the equipment. And so what that allowed us to do is take a small amount of material, get the resin infiltrated in it, and wind either a cylinder or a bottle directly from the yarn.
So essentially what you're doing is you're sort of miniaturizing that process.
Correct. So in order for us to optimize the process using the least amount of material and also getting the process done quickly, normally when we do this type of operation, we use a machine that takes up an entire room. Okay, so we've now downsized that process into a tabletop piece of equipment.
What are the benefits of miniaturizing the entire process?
So several benefits come out of that. One is we basically are tailoring the process that we're developing to the amount of material that's available. We can very quickly rapid prototype in a sense. We can try several different conditions very quickly, changing that using the least amount of material. And also it allows us to modify the machine very quickly to adapt to what we learn as we are winding this material.
When you miniaturize it, are you skipping steps? Because when you look at your device, you don't have many moving parts compared to the commercial
That's correct.
size. And so what have you done to get the same benefits?
Okay, so here are the critical steps, right? You take the yarn, which is dry, and then we need to send it through a bath so that the resin will be absorbed onto the yarn. And then after the resin is absorbed, really what we want to use that infused yarn with is to wind it around the bottle. Okay, so in a very short distance, we're able to achieve that. It's in about a couple of feet, right? We're able to see that process right away.
Now that you have the process that has been miniaturized, what is the next step?
So in order to get our article certified for flight, it needs to be made on a commercial scale. And so those steps that we have defined and optimized are now going to be transferred to a space flight center, which is used to building these types of flight articles. And those basic steps are basically now being adapted back to a commercial machine.
And then from there, that pressure vessel will be transferred to the flight facility where it will be launched on the sounding rocket in 2016.
Correct. We're going to be launching from Wallops, yes.
Now, nanotechnology began several years ago. Well, it's been around for a while, but from where you started with it, how has it evolved over the years?
When we started working with carbon nanotubes, they were still available in powder form. And because on the nanoscale they had such tremendous properties, people thought we could just essentially sprinkle some on a polymer matrix and get the benefit of these materials. We studied it for several years and realized that is not a method that we can get the type of properties that we're looking for, because we're competing with state-of-the-art structural materials, which are carbon fiber composites. So around 5 years ago, we actually switched approach and worked with a vendor so that we use predominantly continuous format of carbon nanotubes. Now, the challenge there is that in the bulk form, it does not have the kind of properties that were existing in the nanoscale. We had to basically optimize the process to take advantage of these processes and work in collaboration with the manufacturer to also optimize those properties from the starting material. So they had to modify their production process to accommodate this. And so there was interactive exchange of information so that we can both get better material properties. In a span of about 3 years, we've made significant advances that take us far from where we started, to the degree that I can say that just 2 years ago we did not have the kind of properties we have now.
And where do you see the future, or how close are you into perfecting carbon nano composites?
So
that's kind of a big question.
Perfection, yes, perfection is hard to achieve. So here's the thing. When you talk about perfection, we are comparing against a material that's been around for about 50 years, right? Although we've come a long way when we actually analyze the materials that we have now for carbon nanotubes, they're nowhere near optimal. The good news is, despite them not being optimal, they're already performing at par with some carbon fiber composites, right? There's a lot of upside to this material that we don't fully understand at this point. And so there's very large areas of research yet that we can explore to really tap the potential of this material.
Now, earlier Steve Gaddis said that they are working for a high reward from high risk. What is the reward you're looking for from carbon nanotube composites?
When we first started looking at carbon nanotubes, the reason we're looking at it is because there's high potential for this material to be a disruptive technology. And the reason is it is multiple times stronger and stiffer than carbon fiber. What we're trying to do now is we are looking to optimize it so that it is at least 2 or 3 times stronger yet than what is possible now. And the reason is there are some applications like access to space, especially if we're going to Mars, where significant reduction of mass is very important, because what you launch is hundreds of times heavier than what your actual payload is. So we're trying to reduce the mass of the payload. If we can get 2 to 3 times stronger than state-of-the-art material, it makes a mission to Mars possible. And that's why we say this is a disruptive technology.
And that is game-changing.
Yes.
You're watching NASA Edge.
An inside and outside look at all things NASA.